All right, this is your first video lecture of the year in Unit 1. And today's focus is going to be on significant figures, dimension analysis, where we're converting from one metric unit to another. And those are some of the introductory concepts in Unit 1. This first unit for AP Chemistry is all review. It's stuff that you've covered either in honors or regular chemistry. Now, regular chemistry maybe not to the degree that honors has. But your textbook, that once you get entered into it, a good practice would be to read it. Read it and look at the example problems. And that'd be something that I would strongly recommend you start doing. Go through, peruse it. If you are unfamiliar with the concept, maybe you actually read it in detail. But most often in a lot of science textbooks, even in college for me, I would just kind of skim it. If it's something that I knew about, I would look at example problem and then I would just move on. But if it was something that I really didn't know much about, I would read it in its entirety. I would look through the sample problems they gave me to really start getting some insight into stuff. So those are the practices you should start implementing this year, especially with not having me in front of you every single day in classroom. You're going to have to start develop things that will help you master this content through your own individual learning techniques that work best for you. All right, the first page of the packet. Now this packet, I put it in two different places. I put it in where it says the module, where it's the first week of school module. I also put it in the one right below that, which is the first unit module. This is the first unit packet, but I wanted it in both positions so that it goes in chronological order. So when you open up this packet, it's PDF. On your iPads, as you listen to a lecture, maybe you can have this lecture up running on maybe a computer screen, and then you can take notes on your iPads. If you much rather have paper pencil, then you could always just take notes on a notebook piece of paper and just use good practice of organizational skills, labeling which one it is. Or you could even, if you want to, print off the packet and then you have your note sheets there, and while you listen you can kind of fill in and do the practice as we go through. Whatever works for you. Now this first page is looking at ions, all right, and memorization. I used to give a quiz on ions where students were, this would be the first major summative quiz of the year where they had to practice memorizing them. This year I'm not going to do that, so don't worry about it. And the main reason why is I have enough to get through. This is an expectation. My expectation is that you will know the ions, okay, both monatomic, which means what again? Okay, there's only one only one element in it. If it's polyatomic, there's more than one ion in it. Most of the positive ions, all of these on the left-hand side are positive ions. Most of these are monatomic ions. The only one that isn't is ammonium. And can anybody remember what the formula of ammonium is? NH4. So one ion contains a nitrogen atom and 4 hydrogen atoms bonded in such a way that it develops a charge. Now, because these are ions, not only do you have to have the formula right, but you got to have the charge right. Does anyone remember what the charge on ammonium is? You will, because it's a very common ion throughout this year. It's +1. So on the old quiz, students had to get the formula of the ion right and also its charge. And it was a pretty simple type of quiz because you knew exactly what was on it. You just had to memorize these things. Because I'm not doing this, my fear is you're not going to do any practice on that. And then when you start having to write formulas and balance equations, you're going to really struggle. So make sure you fill this sheet out. I have a Quizlet in Canvas that you can do practice on this, where I've made flashcards for you already. And you can go through and just do daily practice, a few minutes a day, ripping through these because it's very quick. And just get practice knowing the formulas of both them. And I also have a a practice sheet on knowing your symbols, because some of you might not have had symbols. Now, a lot of the common ones, you're fine. If I say what's the atomic symbol of carbon, I'm pretty confident almost all of you would put down C. But you get some of the harder ones, and I say, what's the atomic symbol of silver? And then I start seeing people do something like SI. SI is not the atomic symbol of silver. Anybody remember what it is? AG. And whenever you have two letters in the atomic symbol, the first one is always capitalized, the second one is always lowercase. You must make sure to do that. Otherwise, you will get marked wrong on the national exam. So, silver's AG. Why? For its Latin name, Latin for agarium. Agarium is Latin for silver. Okay, so that's where a lot of those funky symbols come from. So I've also provided a little practice sheet on atomic symbols that you can do. And again, these are all things that if you're bored, instead of sitting in a study hall, now when you come to school, you're going to have some study hall periods. Instead of just sitting there playing on your games, actually pull up some of the stuff and go through and start practicing and getting practice. And the reason why I tell students to practice, the more practice you do, the better you get at it, and the faster you get at it. The AP Chemistry exam is not only knowing it, but knowing the material fast. All year long, you're going to be hearing me say that. You have to know it fast, okay? Because the more questions you can get through, the more chances you get of getting them right, and the more points you earn, and the higher your grade. So knowing how to do them fast, okay? Over here on the right side are all the negative ions. A few of these are monatomic, and you know when they're monatomic when they end in "ide." When something ends in "ide," it's usually a negative ion that's monatomic. So bromide comes from the element symbol bromine, but it's got a charge on it of -1, so that's bromide. Now there are a few of them that ends in "ide" that are polyatomic, but most of them are monatomic. A very common one is hydroxide. Hydroxide we'll talk about all year long. It's a basic ion. When we do acid-base stuff, hydroxide is oxygen with a hydrogen with a -1 charge. This is the hydroxide. It's a polyatomic ion because it contains both oxygen and hydrogen in a unit, an ion unit. Now, if it ends in "ate" or "ites," then usually it contains oxygen. So nitrite is a nitrogen with 2 oxygens, NO2, and it has a charge of -1. Okay, so you can look these up if you don't know, but I try to go through this list, try to rip out and see how many of them that you know, and then if you're struggling, you can always look them up online. And I'll also have an answer key to this sheet that you can always pull up to and check your answers with when you're done. Or go through the Quizlet. Lots of different places you can do to get practice on this. One last thing about the ions that I forgot to mention, the positive ones, you'll notice the Roman numerals. Does anybody remember what the Roman numerals means? It tells you the charge. So iron 3 means that it's iron, Fe, with a +3 charge. And again, iron, Latin word for ferrum. So ferrum, iron 3 is Fe +3. The Roman numeral tells you the charge on the ion because iron has more than one charge state. And that is true for almost all of the elements that are in the D block of the periodic table, the middle block of the periodic table. And because of that, any element in the middle of the table in groups 3 through 12, those elements we typically always see Roman numeral after because they have more than one oxidation state. Okay, that's the technical word that we use, or you'll say charge. They have multiple charges. All right, so that's the first thing I'd like you to do is just practice this for this week, and do it, keep doing it a week. Do it once a week. Just continue to get that repetition practice, just like your number facts. That will really help you out in the long run. All right, turn the page. So what we're looking at here is knowing the different constants and metric system units. Over here on the left side are some common physical quantities that we're going to work with in this year, and the most common SI unit. The scientific community in the 1700s got together and created specific units of measurement for each of these things that they would all agree upon. Mass is not measured in pounds. Mass is measured in kilograms. That was determined as the SI unit of measurement. So all scientists, when they record something in a journal, will always do so in that specific type of unit. Okay? Amount of substance, which we talk about a lot in chemistry, that's the mole. Okay, mole concept, which we'll talk about more in a year. Electric current, we'll talk a little about electrochemistry, but not towards the end, so don't really worry much about electrical current for right now. And even pressure with the Pascal, that's more for physics. We'll talk about them throughout the year, but nothing you have to really be worried about. All these others are some key concepts that I would probably strongly recommend that you are aware of. Okay, density is something called a derived unit because you've got to take two of these other fundamental units and do a mathematical operation on them, mass divided by volume, to create a quantity called a measurement of something called density. And the most common units for that are grams per cubic centimeter. Grams per cubic centimeter. I do mention this in the paragraph below, which I'd like you to read, but with volume, a cubic centimeter. So think about a centimeter by a centimeter by a centimeter in three-dimensional space. So you create a little cube that's all 1 centimeter in every single edge. That cubic centimeter is fundamentally equal to 1 milliliter. So 1 cubic centimeter is equivalent to a milliliter of volume. So cubic centimeter, milliliter, they are synonymous with each other. Okay? Metric system. Back when you took honors or regular chemistry, the metric system was laid out with all of the different prefixes of measurement. And the great thing with the metric system is when you move from one unit, like C to M, when you move 1 unit, you're moving a factor of 10. So all you have to do would be to move the decimal point. Okay? That's the positive of the metric system, is we don't have to worry about converting 3 teaspoons to 1 tablespoon. So with metric conversions, we can simply move the decimal point. Now, again, this up here is not given on the national exam. They don't give you that. So in this paragraph, again, I tell you the main key units that you should know and be aware of, and you have to memorize what those measurement amounts are. And specifically the ones that you should know are kilo, which is 1,000. A kilometer is 1,000 times bigger than a meter. Okay, milli, mainly milli is for volume measurements. We usually measure in milliliters, and then when we want to do the conversions in the calculations, we want that to convert it back to liters. So we do that in volume. We do kilo whenever we're talking about heat or energy units, kilojoules, which we'll talk about in about October, November. And lastly, light. We look at nano. Okay, the unit of a wavelength, how long a wavelength of light is. We'll look at nanometers specifically. Those are the 3 that I would recommend that you memorize and you know how to convert between them. Okay, so down here, for example, 735 nanometers to meters. There's a couple things. You could look at the factor of nano being 10 to the negative 9th. Okay, or you could look up here and you could look at how many times to move the decimal point. To go to the decimal point of nano, I'm going backwards. The spots in between, those represent a unit of measurement, which they have a prefix name for them, but I just don't care that you know them because they're so very uncommon. So if I move from nano, each time 1, 2, 3, 4, 5, 6, 7, 8, 9. When I go to nanometers to the base unit, which is, you'll see meters, where there's no prefix attached to it, only 1 letter, so it's a base unit, we have to move the decimal 9 times. So right now, 735, the decimal point would be right after the 5. I have to now move the decimal point 9 times to the left, because I'm moving to the left up above on the configuration that I've given you. So when you're done, you're going to have a number that's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yes. So there'd be 6 zeros out in front of it. Or 7.35 times 10 to the negative 7th meters. That's how they would prefer it, but if you had it not in scientific notation, it'd be perfectly acceptable. Okay, so real quickly, if you want to go ahead and do these conversions as practice, you can pause the lecture now, and then I'll come back and I'll have the answers for you. All right, so 38.7 milliliters to liters. You have to divide that by 1,000 because milli is a factor of 1,000. So what you should have is 0.0387 liters. Meters to nanometers. Now we're moving the other direction. I believe, yep, it's -6. Just want to make sure that's what I have here. So if I move it backwards, now I'm going to move a 9 to the other direction. So that's 2 moves. So I have 7 more to go. So there should be 7 zeros after it. 3, 3, 3. So 1.35 times 10 to the 9th. Okay, meters. Joules to kilojoules, again, we're working from right to left, so we're going to move it backwards. 3 kilo is a factor of 1,000, so this will be 25.2 kilojoules. Liters to milliliters, factor of 1,000, but now we're going to go to the right, so that'll be 475 milliliters. And 129 kilojoules to joules, again, we're moving to the right, a factor of 1,000, we move it 3 times, 129,000 joules. So being able to convert through a metric system, moving the decimal point, something that we learned in regular chemistry, something that I would try and recommend that you continue to have practice on if you're struggling with it. Now, application of this is in a mathematical equation. So here's a story problem, which I call plug and chug, because they give you all of the numbers that the student measured. The key equation is going to be given to you in your reference sheet. You look it up, and it says Q equals mc delta T. To find the heat, which this question is asking for, if we're trying to find Q, we have to know the M, which is the mass, the C, which is the specific heat, and delta dt is the change in temperature. To get a change in temperature, we would have to take the final temperature of what it gets to and subtract it from what the initial temperature was. This is how we always get changes in things. So to get the Q value here, we'd have to go ahead and utilize this equation. So this is what I call a plug and chug problem. So go ahead, pause lecture again, figure out what the value is, and we'll see if you got it right. All right, so the mass is 25 grams. The specific heat is 0.387 joules per, that's, my apologies, that is incorrect. 0.387, that should be joules per gram Kelvin, my bad. That should not be moles, it should be grams. My apologies, I'll have to make a change to that. All right, and specific heat is typically in joules per gram. And then we are going from 448 was the final temperature minus the initial temperature of 295. Make sure you subtract first, order of operations, and then you multiply. And I believe with this one, we get 1,480. Now, students would typically stop here, and the reason why they stop here and they think this is the answer is most of my students, they'll plug the numbers in, but they won't plug in the units. And because they don't plug in the units, they think that their answer is it. But here's a tricky question. You'll notice that we have grams and we have per gram. So grams over grams would cancel. When we subtract, we're going to get a Kelvin temperature here. We're going to have a Kelvin temperature and a Kelvin on the bottom. The Kelvins cancel. What are we left with? We're left with a quantity of heat in joules. But what did the question ask for? Kilojoules. And this is where students think they got the question right. They got this point on the national exam, and they lose it because they didn't make sure to keep track of units. So now I've got to still convert this from joules to kilojoules. Kilojoules is bigger. We're moving to the left, so I move the decimal place a factor of 1,000. And we get the answer 1.48 kilojoules. And that's why sometimes students come out of the national exam feeling great, and then all of a sudden they see the score and they're disappointed because little things like that, little mistakes they make in a problem cause them to get it wrong. So you have to be aware of your units. Always plug units into the calculations and see what the unit will be out of the value. Okay? Something just to continue to do throughout the year. Units are so critical. One last thing about a measurement. We'll talk about significant figures here in a second, but whenever you write a final answer for the national exam and you circle or box it, make sure you include 3 numbers in your final answer only. Don't keep writing out 1,487,295. No. Once you get to your 3rd number, stop, round to that number, and report the answer to 3 numbers. And then don't forget to include units with your final answer. Okay, so that's a practice that I'll talk about why later on. Okay, All right, significant figures or significant digits, what are they? Significant figures applies to measurements in science. Whenever we measure something in science, the measurement always contains an estimated digit, one estimated digit. Why? Well, let's look at this example. Here's a beaker that I poured liquid in, and if a student asks, okay, or I ask the student, what's this volume of the measurement? Now, first of all, we'd never use a beaker to measure liquid in a class because it's just not accurate enough. But to measure this volume, okay, to measure this volume, we can tell that the volume is between 10 and 20. We always read a measurement going from smallest number to highest number. So we want to read bottom up because that's how the beaker fills. Okay, so 10, 20. So I know the volume is between 10 and 20. So when I record this measurement, I know with certainty that the number is going to begin with a 1 in the tens position. My next number is going to be an estimated digit. What would you estimate this volume to be? I would say a bunch of you probably would say 17, 18, 19, somewhere in there. 17. Now, if you had 17 and a friend of yours had 18, that's not a big deal. That'd be perfectly fine in the AP exam or any exam in my class. But that last number is an estimated digit, but it's a very educated guess. So we know it's really close to being right, so it counts as a significant figure. So in a measurement in science, all the measurements we have are accurate values. And then last we put on the units, we would say 17 milliliters. This number has got two, what I say is significant figures or sig figs. This value has got two values of measurement in its number, 17 milliliters. Okay, so if I have a number of like 14,820 grams, this number has got four significant figures. And I know that 2 with that measurement is probably the estimated guess. The very last one in the value is an estimated guess based on the instrument itself. Okay, or it's been rounded. This might be a balance, and it's measuring that it's closer to that many grams, 2 grams, than to 1 gram. Okay, so a significant figure is a measurement in science. Okay, now one last thing about significant figures is zeros. If you have a 0 that's after a decimal point, that is an estimated value. We have estimated that number to that 0 point. So 1.40, I know still has 3 significant figures. 1.04, if it's in between, it always counts. So if the value is written down, it counts as a significant figure if it's after the decimal point. If the number is a very large number, like 25,000 joules, these zeros, because there's not a decimal point, more than likely this number has been rounded to the nearest thousand. So because of the uncertainty in this value, zeros only count if there's a decimal point. If there's not, then we would say that this value has only got 2 significant figures. Now, I could continue on. We could do a full lecture on significant figures. I've already kind of gone way too long in this first one, but it's hard with all these concepts in AP chemistry not to try to explain them the best to you. And that's why with these lectures, you can always fast forward, go faster. If you want to increase the speed of this lecture to 1.5, where I'm talking faster, to get through it faster, that's up to you. But I really like to explain concepts for those of you that need to. So I could talk about significant figures left and right all the time, but even to give you practice problems, I'm not going to do that, because here's what I said before on the previous page. Whenever you have a number and you report your answer on the AP exam or any of my exams, you will always round a number. So if you have 148,235.74, whatever the answer is in your calculator, you will always round to 3 significant figures. So the first number is 1, second number is 4, the last number is 8. There's my 3rd significant figure. Your final answer in every AP chemistry exam should have 3 significant figures reported. Okay, right down here. I've even bolded it and underlined it for you. So I would round, since the 2 is below 5, I would just drop it, and there would be my answer with whatever units there would be after this number. I would say the answer is 148,000. if you're not sure, you're like, God, I don't know if I should have zeros there or not. When in doubt, put it in scientific notation. 1.48 times 10 to the 5. If you are ever in doubt if a zero should count, put it in scientific notation. Why? We gain a decimal point, and whatever numbers you write before the times 10, even if it's a zero, it will count as a significant figure. So use scientific notation to your advantage. Okay? If it's a really big number or a really small number, use scientific notation and include only 3 numbers. Okay? Number dot number times 10 to whatever. Number dot number times 10 to whatever. Okay, that's proper scientific notation. I'm not going to review that because if you're in AP Chem, my assumption is you know how to do scientific notation. I'm not going to bore you with that. Okay, if you're struggling with scientific notation, you can go to Bozeman Science or Khan Academy, look up scientific notation review, and you can listen to another lecture and go through practice problems there. That's being a good AP student. You've got to start taking the initiative to work on your own stuff when you know you're struggling and not always trying to seek me out to help explain things. Those are things that you can do. You just got to start getting in the habit of doing them. Okay, so here are 2 practice problems. Go ahead and read them. Pause my lecture again and see if you can get these correct. All right, so a student uses a 50 milliliter graduate cylinder that has markings to the nearest milliliter. Okay, so the graduate cylinder, each mark up is going to go from like 41 to 42. So each mark is to the nearest milliliter. If a student pours 25 mils of a liquid into the cylinder, how many significant figures of precision should the measurement be? So if I get to this graduate cylinder, and I'm measuring about 25, but I've got 26 right below and 24 right below. The scaling, the key thing with any measurement is to understand the scale of the instrument. This graduated cylinder, it's measuring to the nearest 1 milliliter. So if I were to blow this up, let's say 25 was here and 24 was here. And that liquid line comes right in there. This liquid level is between 24 and 25. So because of that, if the scale of the instrument is to a certain value, we can estimate 1 beyond. So if I were using this graduated cylinder, if it's measuring to the nearest milliliter, my answer should contain an estimated digit. So I know it's between 24 and 25, which means I would record here 24.7 milliliters. The last number, that 7, is an estimated digit. Because I was able to go with accuracy, I can kind of divide this up to like 10 equal divisions, and I'm able to pretty accurately guess what that estimated to the 10th milliliter is. I want to use all the precision of that instrument that I possibly can. So whenever you're recording something in science, in this class and lab, think about what are those measurements in? I need to make sure to measure then 1 beyond that point. Okay? So with this graduate cylinder, I can measure 3 significant figures. Okay? All right. Now that number can change in these instruments based on the amount of liquid in there. So here it says if a student measures out 9 milliliters in the same cylinder, well, now I've got 10, now I've got 9, now I've got 8. Let's say the liquid level comes in here. I would, again, I know it's between 9 and 10. It's a little bit above the 9, so I would say 9.2 milliliters. I'm still measuring to the 10th of a mil. But now the number itself, the amount in that cylinder is less than 10, so now this number has only got 2 significant figures. So the amount of material on a scale in a cylinder, that can also affect the amount of significant figures. Okay, and again, with every measurement in science, the last number in that value is an estimated digit. Okay? And that's all I'm going to really go with this material. Again, in this class, whenever you want, report a number with 3 sig figs. However, when you are doing a measurement in class, this concept of 3 sig figs, what I've starred here and circled many times here, this is when we do a calculation. When we do a calculation of our measurements, the final answer will be rounded to 3 sig figs. But if in the class, if in the question on the national exam, it says, what should this measurement be? Do not say, oh, Mr. K always says 3 sig figs. No. Mr. K says when you round a number after you do a calculation, when you round a number, you always report it 3 sig figs. If you're asked to take a measurement in AP Chemistry, what is the scale of the instrument? Go one beyond it. Make sure your final answer has the precision that is required from that instrument. And that's something that's very important. And that's why when you guys do come to chemistry class, okay, we will do lab practice, because that's something you just got to get practice doing. Now, those of you that are all 100% virtual, you might want to, again, go into Google, talk about practice of measuring materials, and find some videos or find some worksheets on that. They usually have answer keys with them. Those are things that you should do and get practice on. Okay, you still need help? Come contact me. All right, the last thing is dimension analysis. Dimension analysis is when we have one unit of measurement and they want a different unit of measurement. Okay, so we are at 515 meters per second. Now, in honors chemistry, whenever you have meters per second, if we have a per unit, I would always tell you to write it with the per unit on the bottom. So 515 meters per second means I've got meters, the unit on top, seconds on the bottom. They want you to convert this into miles per hour. So I've got to change both the distant unit and the time unit. And because I'm changing both, that tells me I'm going to need 2 conversion factors, which, if you remember, are those crossbar symbols. To get rid of a unit of measurement on top, meters, I need to put it in the opposite orientation, and I'm going to replace the meters with the unit of measurement of miles. I can't convert meters into hours. I can only convert distance to distance, length to length, time to time. Okay? Now, it says here 1 mile is equivalent to 1.6093 kilometers. Oops, they tried to trick you, right? 1.6903 kilometers, I need to make sure that's in meters. So I got to go from left to right, and it's a factor of 1,000, so I'm going to move it 3. So it's 1,690.3. So there's 1,690, excuse me, 9, not 90, 9.3 is the number of meters in a mile. The meters will cancel, and now this would give me an answer that's in miles per second. I don't want that, I want per hour. If you have a unit measurement on the bottom, you put it on top, replacing the seconds with hours. Okay, how many seconds are in an hour? Oops, some of you are going to say 60. Some of you are going to say 360. 60 times 60, there are 3,600 seconds in an hour. Again, that is something they expect you to know. The distance measurement, they wouldn't, but the time measurement, they would expect you to be able to convert seconds to hours on your own. Now the seconds cancel, I cross it off, and I'm ready to do the problem. If the number's on the bottom, we divide. If the number's on top, we multiply. So we would take 515, divide it by 1,609.3 times 3,600. This is how we'd punch it into our calculator screen, which I apologize, I didn't do ahead of time. So I'm going to punch this in my calculator. And I get 1152.0536888, and this would be miles per hour. And then I would get a bunch of students that would leave this. Don't leave this number like this. What did Mr. K say? When you do a calculation and you punch in your calculator, your final answer should always have what? 3 sig figs. 1, 2, 3. Round this answer to the 5. We always report the final answer with 3 sig figs. 1,150 miles per hour. And if you were uncertain about that 0, put it in scientific notation. 1.15 times 10 to the 3rd miles per hour. Always putting in scientific notation will give you the right amount of sig figs. Okay? All right, go ahead, try number 2 on your own. Pause the lecture again. Last problem for today. We'll come back. We'll see if you got it right. All right, 27.5 gallons of water per minute. We're changing that to liters per second. Okay, we're going to change both sets of units again. So gallons on the bottom, liters on top. It says there are 3.785 liters in a gallon. Okay, that would give me liters per minute. I want liters per second. So minutes, to get rid of it, goes in opposite orientation. In 1 minute, there are 60 seconds. Looks like I get 1.73 liters per second. Okay. All right, that concludes the lecture. Now what I have for you online is a homework that goes over some of these practice problems to give you extra practice. So you can pull that PDF up. You can go ahead and do the practice homework problems. I have supplied an answer key or homework key for you that you can then check your answers with. I will always take your questions on any of the problems, so you can always shoot me a Canvas notification. But for the most part, this is going to be on you. I'm not going to have you turn this homework in. There will be other homework that you will submit, which I'll talk to you about this week when you show up to class this year. But for this type of homework, when you just get the first set of practice, this is usually just on your own. And again, this is going to be natural consequences. If you don't do a lot of that, you're really going to struggle in this class because you don't get the volume of practice you need to get really proficient at this stuff. So go ahead, do the homework. The homework itself should take no more, I would say, 10-15 minutes of your time, and then check your answers. Really quick, short stuff that you should do. That's a good fundamental practice. I do apologize about the length of this video. I know it was a lot longer, but again, I want to make sure to go into depth that most of you understand. If you want to always watch this lecture at a higher rate of speed, if you want to just pause it and come back to it, break it into chunks. But I will try most oftentimes keep these lectures around 15 minutes. If that means I have to have more of them, great. But again, occasionally I might have to go a little bit longer because some of these concepts are pretty difficult, and I'm doing most of my development of content online at home because I'm trying to utilize class time as a way to go over problems and to give some lab techniques. Okay, and for those of you that are all virtual, that's why I'm trying to do all the content online, is because I don't want you to feel like you're missing out. The one thing you're going to miss out is some lab practice. But if you need, I can always contact you, and I might have some video uploads of me running a lab, and you can just watch it just to kind of get a feel of doing lab, but with having that actual video there so you can see what it would look like if you were actually in the class, so you don't feel like you're being left out at all. I don't want that to be the case. All right, so thanks for listening. Go ahead, try the homework, and then the next lecture is going to be on the next set of pages, which is going to review physical chemical changes and classification of matter.